The goal of this HVAC pre-assessment was to help us as instructors understand where everyone in the class is at with regards to the fundamentals of HVAC in our buildings, as well as help you as students identify any specific areas that you may want to brush up on before we get into using HVAC in our existing building commissioning tasks. So I'll just start with number 1 here. And the idea with this one was to be able to differentiate between sensible and latent loads, or some combination of the two.
And these are the answers that we were looking for. So for things like a heating coil, whether that's preheat, heating, reheat, heat from electronics, whether that's HVAC fans or office electronics or lighting in a building, and for solar gain coming into a building, those really only ever have a sensible components to that load, unlike things like cooking, people, ventilation, air, infiltration coming into a building. We would usually need to consider the sensible and latent component, which has a different set of equations when we start getting into psychrometric calculations.
Question 2 asks, which of these above visualizations represents saturated systems? And by that, we mean which of these HVAC processes has something to do with a phase change from liquid to vapor and can be thought of as a multi-phase saturated system. Well, the first one, certainly when we talk about psychrometrics or the psych chart, there is a saturated line and saturated conditions that we need to consider in those processes as we cool or heat air. Second one, steam processes, absolutely. We have a vapor dome that represents that transition from liquid to superheated vapor. The third one, hydronic systems. If you're doing it right, you shouldn't have a phase change in your hot water, chill water systems. So we need to be able to understand how to read the pump curve, but would not consider that here part of a saturated system. And then refrigeration, very similar to steam. We want to be able to read these enthalpy charts and recognize in a vapor compression system what type of loads and what type of pressures we may be encountering. Question 3 goes right into reading the psych chart and asks, for a single zone air handling unit, which of these sensor readings is most likely in error? So if we assume that the outdoor air condition is correct, we can imagine a process where we are cooling our air and is following a horizontal line to the saturated condition at this cooling coil discharge point. So that would make sense. We can imagine that for most building spaces, that the air that leaves the cooling coil after it sees its processes in the space, the thermostat would read it as having picked up sensible and latent load, and that's more or less what we see here as a diagonal line up and to the right. What doesn't make sense is this return air condition that is at a lower moisture level than any of the other conditions here. So we can presume that the return air condition represents the sensor air. Question 4 has weather bin data plotted on a couple psych charts for these different, very different climates, and is asking if we fixed a broken outside air economizer damper stuck at minimum, where might we expect the most energy savings for something like an office building?
The answer is actually San Francisco, even though it's the least extreme climate of the three. To understand this, let's look at the most extreme climate, Key West, Florida, and try to plot the airside economizing process on the psych chart. We would start this by considering a reasonable zone temperature set point. For an office building, we might be trying to maintain 75 degrees Fahrenheit in cooling mode and assume something like 50 or 60% relative humidity. Now, over the course of a year, return air conditions will vary, but from a design standpoint, we would consider this set point not just as a point on the psych chart, but as a line of constant enthalpy from which to compare all potential outside air conditions. Whenever the outside air has lower energy content or enthalpy than the return air, and we need to condition our supply air, we should be in economizing mode to minimize the load on our cooling coil with 100% outside air. In practice, it's difficult to measure enthalpy, so we would usually see temperature sensors to best estimate if we're above or below some high limit where it's no longer beneficial for an air handling unit in a given climate to stay in economizing mode, and the control system would change the outdoor air damper position to minimum. For Florida, we would expect the fixed dry bulb high limit somewhere around here. And you can see that there's not many bin hours to the left of this line where we would actually be economizing. So having this particular economizer stuck at the minimum position would have a very limited effect on the operation of an air handling unit in this climate. Now we can do a similar exercise in St. Louis, Missouri, and we can see that there's more bin hours available to economize, but we also need to account for times when it would be too cold and we wouldn't be in a cooling mode, and we may even be below a low limit lockout. So this period in the middle here are the bin hours that we would expect to potentially be economizing that we would miss out on with that broken minimum damper position. And finally, we can look at San Francisco, and because it's a less humid climate, the ASHRAE high limit lockout is a little bit higher at 75 degrees. And you can see that the climate doesn't really have a lot of hours near freezing. So pretty much the bulk of these hours we would expect to be in economizing mode. And there would be a fairly significant energy penalty to not being able to economize if we're stuck in our minimum outside air damper position. So even with this concept exercise, blurry seg charts, we can run through this and determine that San Francisco would be the answer for this particular question. Question 5 now has us using the seg chart and trying to quantify some part of the process. So the question asks, what is the reheat load associated with the series of HVAC processes for a 5,000 CFM system? So let's zoom in on the seg chart and just make sure we can read these set of processes. So we know we have mixed air as a start, so we can go here, follow the dehumidification process as we cool the air to the line of saturation, wring out the moisture in the air, end up at this cooling coil discharge temperature. Here it's a low 50 degrees Fahrenheit. But what often happens is when we have a less than design set of loads in the space, we may have met our dehumidification load, but we still may have a sensible load gap. And that's where we expect this reheat load to come into play. So as an opportunity, typically this excessive reheat load and having some kind of a set up for your cooling coil discharge temperature set point, this would be the opportunity. So we want to be able to calculate this. And we need to know, is this a sensible, a latent, or a total load type of situation? Well, as we said earlier, any type of indirect heat exchange with a coil for heating is going to be a sensible process. So we can use the sensible load equation up here on the top right. And now that we can read the seg chart, we can see that the delta T is here and here. And when we plug that in with our 5,000 CFM, we can get the answer of 27,000 BTUH as the load on the reheat coil that we could save by trying to eliminate that excessive reheats and push up the cooling coil discharge set point in a case like this. We're going to move on to section 2 on HVAC heating and cooling equipment. And question 6 asks, which of these pieces of equipment, as shown here, are using indirect heat exchange? And these are the answers that we were looking for. So this was a basic question on the manner of heat exchange in common pieces of HVAC equipment involved in the heating and cooling process in our buildings. Don't worry if the order here tripped you up, as long as you understand the different pieces of equipment, how the two fluids interact, and what type of equations might be attached to that process. Next up, question 7. This is a diagram of the vapor compression cycle inside an air-cooled chiller. And the question is, where's the evaporator in this refrigeration loop? In a simpler cooling system, something like a residential setting or a split AC system, the evaporator would be a coil that would interact with the supply air. In a chiller, whether it's air-cooled or water-cooled, the evaporator is a barrel with chill water on one side and vapor compression cycle refrigerant on the other side. So here we're looking for E to be that evaporator component in this diagram. The other major components of this cycle are the compressor that would take vapor refrigerant from the evaporator and discharge hot gas to the next component of the cycle, which is the condenser, here shown as a coil since it's an air-cooled system. And then finally, the thermal expansion valve that controls the flow of refrigerant into the evaporator based on outlet temperature and pressure. If we're assessing a chiller in a field environment, we want to first identify these four major vapor compression cycle components so that we can then assess other features of a chiller, something like this hot gas bypass, that may have a significant effect on the performance of that chiller. Okay, question 8 asks us to identify which of these components is associated with water-cooled chill water systems, and these are the answers that we were looking for. So 1 and 4 are looking at parts of a water-cooled chiller, and 3 and 6 are different kind of ends of capacity for the cooling tower associated with water-cooled chillers. 2 was the condenser section of a split AC system. 5 is a scroll compressor, which we would usually associate with a smaller capacity chiller, which would typically be an air-cooled chiller. 7 is a reversing valve on something like a heat pump. And 8 is an air-cooled chiller. Looks similar to 1, same vapor compression cycle components, but we have an air-cooled condenser with the fans on top instead of the condenser barrel showed in the water-cooled chillers that then have an extra heat loop or 2 to the cooling tower. Question 9 is another name that thing question. So just going in order here, number 1 looks like a bucket style steam trap. Number 2 looks like a hydronic expansion tank. 3 is what we were looking for. That looks like it'd be the steam condensate tank that would collect condensate from something like a steam trap, maybe at the load or at a certain point in the system, so that that water can be pumped back and used instead of makeup water for a steam system. So you have less waste and you can reuse some of that still warm, preheated hot water in your steam boiler. Number 4 looks like a wall-hung water heater, maybe an on-demand. Number 5 is an air-water separator. 6 looks like a steam boiler. 7 looks like a gas-fired water heater. And 8 looks like a hot water heater, where you see on the left that the gas or maybe oil feed coming in, and then the 2 insulated pieces of pipe. Question 10 is trying to assess our ability to be able to read nameplate data off of heating or cooling equipment. Here we have a package boiler, and the question is, what are the performance capabilities? This is the answer we were looking for. And to understand this, there's 2 important concepts: capacity and efficiency. Let's zoom in on some of these fields. Starting with gross output, we see that this boiler seems to be designed to meet about a 14 million BTUH, or BTU per hour load. So that's what the boiler can do on the high side. On the low side, there is a minimum input that gives us a clue to the capabilities of this boiler. Some boilers, especially older boilers, may have something of a low-high fire, sets of burners that can come on in a 2-stage cycle. Most modern boilers have a turn down where they can modulate to a certain point. Not infinitely, but some ratio that's important to understand. So here, because we see the minimum input is about a tenth of the max input, we would call this a 10-to-1 turn down ratio. Anything lower than this minimum capacity, then we might have the boiler cycling on off, creating wear on the heat exchanger and losing energy up the flue as we have a pre or post purge cycle to clear combustion gases out of that heat exchanger. We also can get an indication of efficiency here. So if we divide the gross output by the max input, we can see that we have a boiler efficiency of about 82%. Now, this would be well below what we would expect with a condensing boiler, where we have a higher efficiency capability out of that boiler, assuming that we have low enough return temperatures. and that would be somewhere in the low to mid 90s. So we know that it's not a condensing boiler because of that efficiency. And what we're looking for with a condensing boiler is an ability for the boiler, through its heat exchanger design, to extract extra energy out of the latent heat of vaporization by condensing water vapor out of the flue gases, and that phase change process puts extra energy into the hot water, assuming that you have return water cool enough, meaning that the return temperature, or the inlet to the boiler, that water temperature is below the dew point of the flue gases to be able to achieve that phase change and condense the water onto the surface of that heat exchanger. So of these options, a non-condensing boiler with 10 to 1 turn down is the most apt description of this piece of equipment. Moving on to pumping systems, question 11 is about the affinity laws and asks which of these parameters has a cubic relationship with horsepower change. So affinity laws, meaning in an ideal situation where the system curve doesn't change, so all of the piping and valve control downstream of your pumps, all things being equal, any change in these parameters would result in a cube law related change in brake horsepower. So this is important as we think about optimizing pumps. We need to know what type of reduction in something like pump speed or an impeller trim or reducing flow, if we can, that has the potential for a cube law relationship change in brake horsepower. Pressure has a square law relationship with flow, which is why the pump curve is built the way it is, and net positive suction head is related more to the safe operation of the pump, making sure that you have an inlet pressure that is high enough to not cause cavitation and eat up your pump impeller. Question 12 asks which parameters on this pump curve are mislabeled. So getting into understanding the construction of a pump curve. So starting with the most important concept to understand on the pump curve is the system curve. So the purple curve is actually the system curve, is this exponential curve that is tied not just to the pump itself, but the system that the pump sees. So you can never have a system curve just associated with the pump. It's associated with the system as a whole, all of the pressure losses downstream. It will move in almost every system. It will get steeper or less steep based on what's happening in that system with control valves, with balance valves. Very important to understand. So that would mean that the red curves aren't system curves, but they are impeller curves, and that's why there's multiple impeller curves. A manufacturer will offer a given pump in different impeller sizes to help the designer select the optimum. You can also take an impeller out and trim that impeller to different sizes, and a degraded pump may operate as if it had a smaller impeller size over time. Also incorrect are the horizontal and vertical axes. They are flipped, so they have the square law relationship backwards. We want to see the x-axis on the bottom as flow, usually in GPM, and the vertical axis in pressure, usually in feet of head. Everything else here is labeled correctly. Question 13 now has us using the pump curve. And one of the typical things we want to do is validate the impeller size on a pump that we see in the field. So the trick here is, one, recognizing which of these values is associated with validating the impeller size and how to convert from PSI to feet of head, which is how we read the pump curve. So it's the deadhead condition, or the second number, the 34.5 PSIG, that is read across the pump. And if we convert that to feet of head using the 2.31 feet of head per PSI conversion, then we get about 80 feet of head, and that's indicating that at a zero flow condition that we are most closely associated with this 9-inch impeller size. Question 14 is about a pump optimization example. So if we find a pump operating at the condition shown, and we know from the documentation that it was designed to operate at this condition, what are the rough brake horsepower savings associated with optimizing this pump? Well, in reading the pump curve, we have to understand that the goal would be to achieve the design or needed GPM. So going off of this design operating point, we would assume that we're trying to meet somewhere a little over 450 GPM. So we don't just read the brake horsepower lines between the operating and the design point. We try to speculate if we added a variable frequency drive or VFD, or maybe if we trimmed the impeller, or perhaps if we got a new pump, what would the brake horsepower savings be from this operating point, meeting our GPM, but at the pressure point associated with our known system curve. And we can see from the lines of brake horsepower, we have the potential to save maybe somewhere from 11 horsepower going down to closer to 5 horsepower. So here we would expect somewhere around 6 horsepower savings for this set of conditions. And finally, last question is about configuration. So with our system diagrams, very important that we can draw, read, and discuss the way that pieces of equipment are piped or ducted together into a system to understand its operation and how it can be improved. So without question, the best term for this chill water system shown is primary secondary. We could go through each of these and understand why we don't have reason to think that those terms or phrases apply here. But the most appropriate way we could talk about this system is constant volume primary with dedicated chiller pumps, variable volume secondary with the distribution pumps on a common header, and 3 coil loads that are all two-way valves. If we discuss the system in that way, we can all be on the same sheet of music for what those optimization, sequencing, and improvement opportunities are. Moving on to airside systems. This first question asks us for descriptions of what you see. These are the answers that we were looking for. The most appropriate descriptions are that yes, this is a centrifugal fan as opposed to a prop or propeller or axial fan based on the orientation of the drive shaft and the centrifugal action where the air movement is perpendicular to the drive shaft rather than being axial or in line with the drive shaft. A vane axial fan is just a specific type of these axial fans that uses guide vanes to control the airflow. Now that we have VFDs is more of a common way to do that. Those are often opportunities to take out the guide vanes and remove that pressure drop and control things a little bit more efficiently. We do have an indirect drive system, meaning that the drive shaft of this squirrel cage blower, named because it looks like a hamster or a squirrel could be running around in there, has a belt between the pulley on the drive shaft and the pulley on the motor. It doesn't have to be that way for a radial or centrifugal fan, but here we do have a little bit of extra loss and another opportunity to optimize the system to make sure we're using the right kind of belts at the right tension. Double width double inlet is a term for a piece of equipment where you have 2 of these blower assemblies or squirrel cage blowers that are effectively connected together, and you can have inlet on either side of the fan. That might be the case here, so if you put that, I would say that's fine. It's tough for me to tell here, and the reason that can matter is if you have a double width double inlet fan and you have stratification in your mixed air plenum, that stratification, depending on the orientation of the mixed air coming in relative to where these inlets are on the fan, that stratification may carry through on the supply of this blower, and a supply air temperature sensor may not pick up the correct mass weighted average airstream temperature based on that stratification that could persist in a double width double inlet system. Okay, question 17 asks, in this fan energy equation, what are some possible situations that would contribute to the efficiency term in the denominator of this fan power equation modified to include operating hours and generate a kWh number? So a lot of existing building commissioning energy estimates will use a simplified version of some conservation of mass or energy formula. Here we have some conversion units for standard air conditions, as well as some unit conversions for power. And these are the answers that we were looking for. So everything highlighted here is built into that efficiency term. So everything from loose belts or the wrong belt to an old motor or a non-NEMA premium efficient motor or motor bearing issues, the fan itself, so some hydraulic losses that are just built into the fan operating and maybe not at its peak efficiency point, as well as if you have a VFD, it's going to have some electrical losses given off in the form of heat if you're standing next to that VFD. And those all contribute to giving a fan power efficiency term that may be around 60% efficient. So sometimes we underestimate our energy savings when we don't acknowledge those inefficiencies that are built into the system. Or in R6 finding, we could go after these efficiency terms themselves. Economizer damper failure wouldn't directly contribute to that efficiency term, although there may be some psychrometric calculations to account for the effect of that poor operation. And duct distribution pressure drops would be expected to change the inches of static pressure term in the numerator, but not directly the efficiency term in the denominator. Question 18 shows us a piece of airside terminal equipment. This is a VAV box, variable air volume box, and it's asking what features or what components can you see on this equipment. So these are the answers that we were looking for. The first one might trip you up because you see pneumatic tubing coming out of the inlet of this box, the red and the blue tubes coming from this flow ring, and they're taking air measurements, but it's not pneumatic control. You see a DDC or electronic controller attached to this box, the orange controller, and it has a integral damper actuator, the shaft coming through here. The controller is going to take the flow coming in and make an adjustment to the damper to try to maintain a set point for the airflow, and we call that pressure independence. If we can maintain the flow independent of the pressure in the supply trunk, that would be a pressure independent VAV box. Just one inlet here. You can have dual inlet boxes. No special fan, no series or parallel fan box. We do see a reheat coil on the downstream side of this box. So this is a pretty vanilla thing that we would see. So I'm guessing everybody watching this video has one of these in one of their buildings. So we need to know how to operate them best, how to get points from them, how to trend their performance, and what type of quirks we may want to test for to make sure that this system and the overall airside system that this VAV box is a part of is operating at its peak in all demand conditions. Question 19 asks, based on the limited information here, can we get an idea in theory for how cold it would have to be for our preheat coil, shown here, to see freezing conditions? So this is really just a math problem to look at the weighted average of mixed air given this ratio of outside air and return air. So the equation would look like this. We would have return air times the percentage of return air flow plus outside air temperature times the percentage of outside air flow. And when would that get to freezing conditions? When would that equal 32 degrees Fahrenheit? Well, when you do the math and you plug these numbers in, you actually get a pretty low temperature. It would have to get negative 82 outside under these conditions for the preheat coil to see freezing conditions. Now, of course, that's in theory. We don't always have perfect control at our economizers. We might have a damper failure. We might have stratification. So we need to be prepared to protect our cooling coil. However, we want to make sure we're doing that intelligently with the least burden to a preheat coil, or perhaps considering certain climates where a preheat coil is not likely to be needed and that pressure drop is just going to cause a burden to the system without any benefit. Question 20, finishing the airside system portion, is asking, based on this plot, what can we say about the condition of the airside economizer? So, like we've been taught, just trying to interpret this chart based on its main elements. We have an x-axis of outside air temperature. We have a y-axis of mixed air temperature. And the curve that we see here with these different colored lines is what's sometimes called the perfect or ideal economizer profile. For something like an integrated economizer, that can still operate as dampers and mechanically cool at the same time. And with this specific ratio of minimum outside air required, we would expect the dots on this chart representing individual instances of it's this temperature outside, and at that temperature, at the same moment, it was this other temperature for mixed air. So we should be following the plot. Why aren't we, and what does it mean? How do we interpret it? Well, the answer here we're looking for is that the return air is overused. And the way that we can think about that is that we would expect that we're going to be on minimum air when we're on the green line up here, and we are on the orange line here, where we tend to follow that curve in areas that we have outside air conditions where we can economize while we're cooling, or economize and modulate the dampers to meet the mixed air temperature set point here somewhere around 52 degrees. Where we hang on that minimum air line indicates that we're overusing return air. So these plots are very, very helpful to be able to quickly visually identify a problem with the economizer as well as the diagnosis for what that problem is. Question 21 is asking what is true about this HVAC control response shown. So, a lot to talk about here, but these are the answers that we were looking for. This is called hunting. If you ever sit and watch a valve actuator or a damper in a mechanical room kind of go from one side of its range extent to the other, we would call that hunting, and that's usually an opportunity to tune some kind of control loop, a PID loop or a PI, proportional integral loop. There's some other things that are mostly true here about what to do about that. So a lot of people that do loop tuning in the field in HVAC will try to get to this hunting point and then reduce their proportional gain maybe by half, and then keep adding integral gain until you can have an overshoot that's acceptable. I wouldn't say that these typically would have any kind of an occupant complaint issue. Usually this is more about equipment wear and maybe some kind of energy waste. But HVAC is very tolerant of this kind of poor controllability. So that is why these kind of band-aid or hidden issues are the kind of things we look for in existing building commissioning. Derivative control. Derivative control should almost never be used in HVAC. It's just not worth the potential risk for trying to predict an overshoot or a correction. And that's why most HVAC control really is just P and I. You might call this floating control. This actually does look similar to like in a residential environment. You might have a heating set point and a cooling set point, and you might get past your cooling set point, start cooling until you get to the heating set point, and then start heating. But the profile of this, I would say, isn't necessarily exclusive to floating control, and we're usually looking for this where we have PI loops and are identifying a loop tuning issue. Question 22 shows us, for an example brand, a number of different HVAC controller models and asking what we think the HOA functionality is. So the first key to this is knowing what HOA stands for and what it means. HOA is handoff auto, and that could be on something like a motor control center, or it might be on your HVAC controllers. So typically you can select a model that has some kind of an interface on the controller itself where you can override or turn off some output. So typically we want to do this from a front end control in a more easily monitored fashion. However, it can be very handy for functional testing to have something like controller 1 or controller 2 where you have either a digital interface or you can have these toggle switches that allow you to override the output, whether it's binary or analog. And typically there might be a screw that you can change on that Model 2 with the toggle switches to change the output to whatever extent on something like a 0 to 10 volt range that has been provided. But these are important as we specify control systems, as we assess systems in the field to think about the functional test needs and how we can accomplish those. Okay, question 23 asks us to interpret this logic block diagram. This is important because we may get submittals from our controls designers that look like this. And of course, the logic that lives in our HVAC controllers will usually have an interface for configuring those controllers that is this type of programming structure. So reading and communicating is important. I like to start from the right and work backwards. So what's being controlled? Well, a VAV damper command looks like the output signal. And that shading on this arrow here indicates that this is connected to some hardware output. Upstream of that is this PID loop or PID block. We're just probably using PI control with some associated configurations for the parameters of that PI control. But what we can see here is that it's enabled under a certain set of circumstances. If we follow back to this Boolean block, this is an OR block. And what it's saying is that if my system occupancy, probably for the air handling unit, is in anything other than unoccupied, or I have a zone occupancy command, and that's probably like a local thermostat push button override, this binary hardware, then I can enable my PID block. Otherwise, be at minimum. On the left of this PID block is what we're trying to control to. We're trying to control VAV supply airflow, SA-F. And what we're controlling to is a function of the zone temperature set point deviation. So the greater the zone temperature set point deviation, based on this minus block, a reset schedule is built in here that will increase or decrease the supply airflow set point that box is trying to keep to. So all that means is the amount of airflow that your VAV box is going to try to bring in from a heat and cooling standpoint is going to be tied to how off from your zone temperature set point you are. If it's getting way overheated, you're going to bring in more air, assuming that that air is conditioned and can cool down the space. So let's look at our answers. First thing is the control loop uses 7 hardware input-output signals. No, based on the convention from our unified facility criteria. Everything with a shaded portion of the block is the hardware, so I see 4 hardware input-output signals, 3 input, 1 output. When unoccupied, the VAV damper closes. We don't actually know that. We know that there's a minimum associated with that VAV box. That minimum could be configured to 0. But it's not guaranteed based on this logic block sequence. The box requires system occupancy and zone occupancy to enable control. The key word in there is and from a Boolean logic standpoint, those terms really matter. So what this symbol is indicating is that this is an OR condition. We need system occupancy to be other than unoccupied, or we need that local zone occupancy override at a push button like a thermostat. Zone temperature set point, is it being reset? Doesn't look like it here. It may be reset elsewhere, but from this logic block sequence, what's being reset is supply airflow, set point. The box is pressure independent. Yes, I would say so. Anytime that we are controlling to supply airflow and we have an analog signal that we're bringing in to then compare to that set point, we have the ability to control that airflow independent of the pressure in the supply air trunk upstream. Zone airflow is a function of zone temp deviation from set point. Yes, I think that's absolutely the case here in the way that zone temperature from an analog condition is being compared with the set point, and based on that difference is driving that reset schedule to determine the supply airflow set point going into that PID loop. So a lot here. It can be even more complicated looking at a controller that has about 50 of these, but very important that we can read these to know what our system is doing and how we want it to operate better. Question 24 asks, which of these HVAC control drawings is most likely to contain protocol-specific information? So terms like BACnet and LawnWorks and Niagara Framework Fox control, or even OPC and Modbus, a lot of times those terms tend to absorb the conversation of what HVAC control is. So certainly we want an open system where we're using standard protocols and we can switch controllers out. However, there's a lot more to controls than the protocols in use, and we would expect that our HVAC control design process and the deliverables that come out of that are largely devoid of protocol information. An exception for that is the point schedule. So here, per our unified facility criteria and specifications, we want to have a lot of information that indicates the controller ID, based on the protocol in use, if there's BACnet object types that we want to make sure are recorded, if there's any specific routing that has a protocol component to it, if there's Niagara IDs, we want to make sure that all of that is contained in a document that can pass from your building level controller to your UMCS integrator. Other than that, we should be able to understand the rest of the control of the system from these control logic diagrams or the schematics or the ladder diagrams where things are hooked up to the motor control center. None of those should contain protocol specific information. And finally, we have a question about a UMCS front end, or utility monitoring and control system front end. So all of your building automation ideally is networked to a single front end so that you can do things like look at trends, set up alarms, configure schedules, and look at the graphics to understand the operation of your system and improve it. These are the answers we were looking for. Very important to understand two things. One, by default, there's no reason that a system that's hooked up to a front end is automatically going to be more energy efficient. It has the capability to do many advanced things, but by itself will not accomplish that. That's where we come in. Two, having a front end certainly may ease the retrocommissioning process, but it is not required to perform any RCX tasks. We can supplement with data loggers. We can monitor the system without getting into the logic or looking at the schedules. There's a lot we can infer, a lot we can assess for. Certainly makes it easier to understand that operation and make improvements, but it doesn't disqualify a building from being an RCX candidate. Everything else here hopefully is self-explanatory, but certainly UMCS has a strong role with our RCX and something we want to include in our assessment and our improvement list. So depending on how comfortable you feel with some of those answers, you may want to go and brush up on some of those specific HVAC fundamental areas on this set of resources we made on YouTube at RCX University. And there's also a copy at Miltude. If you have any continued issues accessing these, please let us know. We can send you the original video files. If you found yourself disagreeing with some of the answers there, maybe something about the controlled tuning or a psychrometric element, you feel like there might be a different way to look at it, that's fine too. That probably means that this HVAC pre-assessment indicates that you're ready to start playing with this stuff more specific to the RCX process. So please feel free to visit here if you need to. This is very much choose your own adventure. If there's certain concepts or certain topics that you want to brush up on, but this is voluntary and it's just here to help you succeed in this retrocommissioning course.